So like I can know before I design for this, whether what I'm doing,
whether your process, yeah.
Yeah, whether my process
was
is correct.
equations or the.
All right, shall we get started? Sorry. So, ready for more? How did it go on Monday? Lifeng? Did it work? Oh, yeah, I will quickly recap those things anyway. Oh, I just got a question on Piazza. I will cover it in the recitation, some example code for the sparse matrices. It's not a big deal anyway. It's like a simple thing. It's just something I forgot to mention, but I will tell Shao to mention it on the recitation. It's not a big deal. You can easily do the homework without it.
Also, do you have any other copies of the? Oh wait, are you talking about the example code for the one that was due Friday?
Right.
Okay, so we don't need the example code.
Not really. I will get it to you, but it's not totally critical. Okay, so let's recap the things you should have learned the last time. So what is a span? If I have a set of vectors v1 to vk, what is their span? I think I even said it before, right? Oh, my thing's not good. We got it, right? Oops. That's nice. All right. So, what is it? They are all linear combinations, right? So I can pick any alphas and take arbitrary linear combination. So this thing is called linear combination, and if I take all of them for all alpha 1 to alpha k reals, then this is called the span of the vectors. So when are the same vectors, so B1, linear independence, let's just recall these notions. Those are like critical terms in linear algebra, so you need to remember those. So when they are linearly independent, or just independent, or Li, I want to write it for short. So how is it defined? Yeah?
It's when the only linear combination of them that forms a zero vector is.
Exactly. So there's always like a funny way how to formulate it, like the only one, right? So one way you can formulate it, you can say that if this linear combination, again, same idea, if this linear combination gives me 0, then this implies that all of these alpha must be zeros, right? So this is like, here is like equivalence and here is like implication. But that's exactly just what you said, right? What you just said. That the only one that will make it 0 is the trivial one, which will always make it 0, right? So that's the important distinction. If it's a non-trivial one, we say that they are linearly dependent, right? And you should know that if they are linearly dependent, it means that we can express one of the vectors as a linear combination of the others. Did you do that? Do you know that? So if they are not linearly independent, they are linearly dependent, right? So if they are linearly dependent, then I can find one which can be expressed as a linear combination of the remaining ones. Beta j vj. So this means I'm summing over all these except for the number I, right? And that's because if one of these alphas is non-zero, so if they are linearly dependent, that means that there exists a non-trivial combination that gives me 0, right? And that means that at least one of these alphas, maybe it's better if I write it like this, alpha 1 v1 plus alpha k vk. So it means that if the combination is non-trivial, at least one of these alphas must be non-zero, right? Let's say it's some alpha j is non-zero, and then I can divide by it, right? So this is 0. If I divide the entire thing by alpha j, I get alpha 1 divided by alpha j, plus there is vj, but there's going to be just alpha j divided by alpha j, which is 1, right? plus alpha k divided by alpha j, bk equals 0. And then I can just put, this is just 1, so I can put this on the other side, and you can clearly see that I have vj expressed as a linear combination, right? So if I should finish it properly, then vj is minus alpha 1 divided by alpha j, v1, minus, and so on. Now I'm skipping the j, that's what I meant in this sum, up to the last one. And the critical thing is that I had one non-zero coefficient with which I can divide, right? If they are linearly independent, all the coefficients have to be 0 to give me 0, so I cannot apply this. So this is only true if they are linearly dependent. And that's I guess why we call them dependent, right? That means that one depends on the others, because you can like write it as the linear combination of the others. Okay, so that's linear independence and span. So like very, very basic notions in linear algebra. And using them, we can define what is a basis, right? So v1 to vk is a basis when? Do you remember that? Hopefully Frank do a good job. Yeah, sure.
I think when you can represent any vectors in linear combination of them.
That's right. I should actually say basis of what, right? So I should say basis of V, where V is some vector space, right? So you're saying that if I take arbitrary vector from the vector space, then I need to be able to express it as a linear combination of these vectors that are aspiring to be basis vectors. And there is another condition, that's condition number 1. So this one we can say also, we can say that the span of V1 to Vk is V, right? That's like a brief way to write it, because I define the span, that's the subspace, you had subspaces, right? So this is the subspace of all linear combinations. And if it wants to be a basis, then the subspace of all linear combinations must be exactly the whole V. So that's condition number 1, and there is another one. Who remembers? Anyone else? This is not sufficient for this to be a basis. The other condition is that they have to be linearly independent. Or Li meaning linearly independent. So there are 2 conditions for like a set of vectors to be a basis. They have to span the entire or generate the entire vector space. So any vector from V I can write as their linear combination, and then must be linearly independent. Why do I want the linear independence? Is sort of obvious, right? Because if I had like one that was linearly dependent from here, then I could take it away, right? So that's sort of stupid, right? So that's why we define basis as like the minimal set of vectors that generates the entire space. And from this we can define dimension. Because there was this I guess theorem or something, lemma, which says that every basis has the same number of vectors. So in any vector space or subspaces, you can have a bunch of different bases, right? There is no shortage of bases in linear spaces. And every basis can be different, right? We talked about the standard basis. That's the simplest one you can think about, like these folks. But a different set of 3 vectors, many other combinations are a perfectly valid basis, right? The important thing is that every basis has the same number of vectors. This k, if this is a basis of V, then the k has to be the same everywhere, right? I think that's what you discussed on Monday, how to prove this. It's not so difficult. And then that means this number of basis vectors is a characteristic of the vector space, right? It's something inherent to the vector space. And that's called dimension. So this k is the dimension of the vector space V. So the dimension is sort of intuitive. I think I was saying it intuitively before, right? If we have the linear space R to n, then its dimension is n, right? It becomes a little more interesting when we talk about subspaces, because so if I have subspaces we also talked about on Monday, right? So if I have like R2, so let's say I'm in R2, and I have this line passing through the origin, and that's my subspace. What's the dimension of the subspace? Very no trick question here. 1, exactly. So if I was in 3D, I can have lines that would be one-dimensional subspaces and planes, which would be two-dimensional subspaces. And 3D, the entire space is three-dimensional. Oh, a slightly tricky question. What about this in R2? Line not passing through the origin. What is tricky about this question? The tricky thing is that this line not passing through the origin is not even a subspace, right? Because a subspace needs to be a linear space by itself, and linear spaces always have to have 0 in them, right? Because there is the property that if you take a vector from a linear space and you multiply it by arbitrary scalar, then you need to still be in the linear space. And that scalar can be 0. So if you multiply by 0, you get a 0 vector. So the 0 vector has to be there. So this is not a subspace, not a linear subspace. Then we could talk about like affine subspace, which means that after we translate it back, then we get a linear subspace. But that's something slightly different. I'm not going to go into that now. By the way, linear spaces don't always have to have a finite dimension, which is sort of funny. Here, all the vector spaces we have been dealing with so far, they had finite dimension, but they don't, right? If I take the space of functions defined on the interval 0, 1, continuous functions, for example, then we said that this is a perfectly valid example of a vector space, right? But it has infinite dimension there, because there is no finite set of basis vectors, because there is just so many functions intuitively. Now, if you take polynomials, as we were doing earlier on, if I say that my ft needs to be like this, for example, then this becomes a finite dimensional subspace of this infinite dimensional space of continuous functions. And this is essentially the basic idea of finite element method, or Galerkin methods. But we will get to that maybe later. Okay, so the important thing for now is looking at matrices, understanding a general rectangular matrix, a real matrix m by n, which can either look like this or it can look like this, right? Or can even be square in the general case. So the subspaces play there an important role. Let's slowly get to. So if I have a matrix, let me copy that, m by n. So the column space of this matrix is, what is the column space? So maybe we could first say it intuitively, right? So if I have a matrix that looks like this, has some columns, A1 to n columns, right? M rows and n columns. So can you tell me what is the column space of this matrix? It's again, these things are terms that you need to remember, because like terms like orthogonal, they basically like almost made it to common speech, if a little bit nerdy speech. Like if you say like something is orthogonal to something else, it means like it's not related to it. So column space is probably not used in English so often, but you still need to remember what it is. So what it is, if this is my matrix. Exactly, yes. And in matrix language, I can write it, they are all vectors y, such that y is formed as ax, right? And y is a result of multiplying a by x, where x is an arbitrary vector from Rn. So I take an arbitrary vector x, and that's exactly doing the linear combination of these columns. Do you see it there? I would really like you to get the geometric intuition, when I multiply the matrix by the vector, I'm just doing a linear combination of all these columns. If it's not clear, I can write it out. Shall I write it out? Huh? No. Okay, good. So that's what the column space is. There is another and it's fairly simple to see that this is a subspace, right? For a subspace, it means if I take two vectors like this, they are still going to be in the column space. That the scalar multiple will also be there. That's like trivial, right? If I multiply the y by something, that means I can as well multiply the x by something. So it clearly is a subspace. And zero will be there, right? For if I put x as 0, then y is 0, so I'm good. It is a linear subspace. Like very, very quick proof, but should be clear. Again, if it's not, I'm happy to explain better. So what is null space? Another very important space. So the column space is sometimes denoted as CA. That's what we'll be using, column space. The null space, NA, is what? Somebody can tell me? See if you remember that one. Yeah?
It's a set of vectors that A maps to 0.
Exactly. So those are those x's such that AX equals 0. Again, x is from Rn, so that this multiplication is even defined, right? And this is NA, this is CA. So this is exactly what we were talking about on Friday when we are talking about how to characterize the solutions of a linear system AX equals B, right? And we were saying that we can find one particular solution and then the set of special solutions where we say that the B is a 0. And the set of the special solutions is exactly the null space. And it's again a linear subspace, as it's again very easy to verify. If you take two vectors from the null space, then their sum will be in the null space. If you take one vector from the null space and multiply it by a scalar, it is going to be in the null space. And 0 obviously is in the null space because if I hit A with 0, I get 0 back. All right. So those are the subspaces, and now we know there is a basis in every linear space, so it means also in every subspace, right? Then I could be asking, what are the bases for the column space and for the null space, right? So how do I find, the basis for the column span? So what can I do? What I can do is convert the matrix to the reduced row echelon form, which is going to look like something like this. These x's are just arbitrary numbers. So remember the reduced row echelon has like this staircase pattern. And there are zeros everywhere here. There can be like arbitrary number of 0 rows. So this is my reduced row echelon matrix. And now if I want a basis for the column span, that's from here it's very simple. All I need to do is take these vectors. The vectors corresponding to the pivot elements. It's clear, it's easy to see that these vectors are indeed linearly independent, right? Because if I take vectors 1, 0, 0, let's say there is 1, 0 row, 0, 1, 0, 0, and 0, 0, 1, 0. Should be obvious that these are linearly independent, right? Because if I do the test, this was supposed to be gamma. This thing is gamma. And if I say this has to be 0, then obviously this implies that from the first equation that alpha has to be 0, beta has to be 0, and gamma has to be 0, right? And that's exactly the condition of linear independence. So these vectors obviously are linearly independent, and then they generate the entire column span, because every whatever is here I can write as a linear combination of them. And here there are just zeros here, so there are zeros no matter what I multiply it with. So that's how I can get the basis for the column span. The basis for the null space can also be defined from this. I think I will better show that on an example. I think it will be a little more clear on an example. So let's define the two remaining important spaces. So there is a row space. So row space is like column space, except that I will be multiplying the rows. I will be taking linear combinations of rows of the matrix as opposed to columns of the matrix. So there are two ways to write it. So if I have the same matrix as before, but now I'll be looking at its rows like this. So it has m rows. So the linear combination of the rows I can write like this. So it'll be like some coefficients of my linear combination. And this is a matrix product. This is like a row vector multiplying this matrix, right? And this is again doing nothing but a linear combination of the rows of the matrix, right? So the row space is nothing but a span of all the rows of the matrix, right? The column space was a span of all the columns of the matrix, and the row space is the span of all the rows. Quite obviously. And the way it works, so if I wanted to get column space, I had to multiply every column by something and sum it. And in matrix form, it's written this way. And the row space in matrix form is written this way, right? Here would be the first coefficient for the first row, and so on, the last coefficient for the last row, right? So if this was my matrix A, this is actually the matrix transposed. No, sorry, this is still A. This is some transpose vector X, because it's a row vector. I said by default we have column vectors, so if you need to do with the row vectors, we transpose them. So the row span is the set of all vectors y transposed. That's because this will be a row vector, so I transpose it so it's column vector, such that yt is xta for arbitrary x from R what? Rm, right? Because the number of rows. So do you understand that? This is the definition of the row space. Is it clear why I'm doing this playing the transposition game here? Because if I multiply this, I will get this as a result, right? And I said that by default we assume that our vectors are column vectors. I think MATLAB assumes the same way by default. So I need to transpose to get back to column vector. Also, this whole equality we can transpose, right? Because this is just a matrix equality. If we transpose both sides, they still have to be equal, right? So this is equivalent to saying that y is atx, right? Or here I have transposed xta, transposed is atx. Yeah? So that means that the row space of the matrix is actually nothing but the column space of AT, the matrix transposed. Sort of makes sense, right? Because if I transpose the matrix, then rows become columns. So if I transpose the matrix, so my AT is this, A1 to AM. And now if I take the column space of this matrix, it's the same thing as taking the row space of the non-transposed matrix. Make sense? I hope so. So this is the third important subspace associated with any arbitrary matrix. And actually, yeah, this so all this stuff is summarized on this slide. The row span business. So that the row sometimes the row space is called also row span, and it's the column span of A transposed. And this is again how we can get it. We can again read it from the reduced row echelon form of R. So if we convert the A to reduced row echelon form, where R is the reduced row echelon version and E is the matrix corresponding to the elementary row operations, then what that means is that every row of A is a linear combination of rows of R. This is really the point of the elementary row operations, right? Because notice that all the elementary row operations are doing is linear combinations on the rows of the original matrix. They can be multiplying a row by scalar, that's fine. They can be swapping rows, also doesn't matter. And they can be adding a multiple of one row to another row, right? All these things are linear combinations. All these things can be encoded by this matrix E, which is invertible. So what that means is that the row space of A is the same as the row space of R. So that means that to read the row span, it doesn't matter if you work with A or R. So we can convert to the reduced row echelon form R and figure out what the row space is there. And how do we figure it out what the row space is in R? Well, we again look at the pivot rows of R. So I guess I could again, maybe I can show it on this image here. So if I'm in my reduced row echelon matrix, and I want to find out what is the basis for the row space, then I simply take the first R rows which correspond to the pivot elements. Those are, so if this is the R is the rank of the matrix, right? And the remaining ones have to be 0. So these vectors, they generate the entire row space of my matrix. Why? Because it's the same. The row space of my matrix A is the same as the row space of my matrix R. And it's a basis because these vectors are clearly linearly independent, right? That's because of the stir shape pattern, right? If I write a linear combination of these three things and I want this linear combination to be 0, the only way to achieve it is by zeroing on everything, right? Because here I have here I again have the identity matrix. So it's the same argument as here. So this is basically what is summarized here. And the important thing, and that's something interesting actually. So if we look both at the row space and the column space, they have the same dimension. In both cases, we get R linearly independent pivot rows or columns. So the dimension of the row space is equal to the dimension of the column space, and in both cases is equal to the rank of the matrix. That's what this R means. So this is written here. This is like the dimension of the subspace. So it doesn't matter if you are looking at the row span or column span. In both cases, the dimension is equal to the rank of the matrix. I will do an example in a little bit, which will shed some more light on this. This like sounds like theoretical, and but if you look at some specific matrices, that starts making more sense. Here is just a summary of what I was saying before about the null space. So the null space is the set of all vectors such that AX is 0. And what is the dimension of the null space? That's an interesting question. So the dimension of the null space are all these vectors, right? And they will be generated by all the special solutions. That's what we discussed on Friday, right? Once you do the reduced row echelon form, you get some pivot variables and some free variables. And the number of free variables will be exactly n minus r, right? And for every free variable, we can get a solution here. And the solutions we get for the individual free variables will be linearly independent. So we will get a subspace of dimension n minus r. Again, why is it that the special solutions are linearly independent? That's because how we are picking them, right? If I, again, yeah, I will show it on an example. The point being that, like, let me just explain it here. If I have my free variables like x2, x3, I don't know, x5, for example, then the first choice is this, the second choice is this, and the third choice is this, right? And then I get some other values from x1 and x4. But it doesn't matter what I get there, because already these zeros and ones, they guarantee that these vectors will be linearly independent. Right? Once this like identity matrix pattern appears there, then linear independence is guaranteed from that. Which implies that the dimension of the null space is n minus r. So the number of columns of A minus the rank. That's the dimension of the null space. You can also invoke the concept of orthogonality and realize that this actually means that all the vectors x that are in the null space are actually orthogonal to all of the rows of A. That's exactly what this means, right? Because if I multiply x, that means multiplying every row of A by x, right? And if it's 0 everywhere, it means that the x is orthogonal to all the rows of A, which means that x is in the orthogonal complement of A. Oh yeah, that's written here. So let's summarize this. So we have n minus r linearly independent vectors which form the null space, which form the basis of the null space of matrix A. They are all orthogonal to the row space. The CAT is the row space. The row space has dimension r. So what it actually means is that we took the original R to n space and we split it into two parts, into the null space and into its orthogonal complement, which is the row space. It might not be making a whole lot of sense without like seeing a specific example, but like just hanging there, or it should all come together in a little bit. The final piece I need here is the left null space. So that would be like the fourth case of a subspace. Yeah, here I had, maybe I can explain it here better. So we had for every matrix we had a column space, null space, row space, and the fourth thing is so-called left null space, which won't be anything else but the null space of AT. You might be like anticipating that, like for symmetry purposes, right? Because this transpose appeared here, so the transpose should also appear somewhere in the null spaces. So this like completes the picture. And the point of the left null space is it's a set of all vectors such that ATY is 0. All vectors y such that A transpose y is 0, right? So returning to my drawing here, what does that mean that ATY is 0? I can also write it as YTA being 0, which means that if this is my A, that means that if this is my Y, this is my Y, this is my A, that means that all columns of M multiplied by Y have to give me 0, right? So the idea of a null space was if I multiply it from the right, I get 0, and the left null space is called left null space because if I multiply it with the left by some vector, I get 0. And again, by a similar argument, basically repeating the same reasoning, but now on AT as opposed to A. So we can find my M minus R special solutions if we are looking at this system. The only difference being that we are now considering the transposed matrix, right? So instead of N that was there for A, we get M here because AT has M columns. So we get M minus R special solutions, linearly independent vectors. And again, they are orthogonal to the columns of A. So this is really just like looking at the same thing transposed, like from the other way. So the left null space consists of, is generated by M minus R linearly independent vectors. They are all orthogonal to the column space. The column space has dimension R. So it means that in this case, we took the space Rm and split it in two parts. The M minus R dimensional part of the left null space and the R dimensional part, that's the column span. And these two things are orthogonal. The one is the orthogonal complement of the other. So I guess let me try to do an example, because I think it's much easier to see all these things on some particular matrix than in full generality. So let's take a matrix that looks like this. Let's take a simple one. That's 0, 0, 0, 1, 2. So this is already in reduced row echelon form to simplify things. So these are my variables. So this is 3 by 5 matrix, right? And the pivot rows. So this would be the pivot rows. The pivot columns. Pivot rows are these. Right, so the first two rows are the pivot rows, and the column number 1 and column number 4 are pivot columns. So you can immediately see the rank of the matrix. What is the rank? 2, right? Because I have 2 pivot elements there. Which tells me that the dimension of the row space and column space will be 2. So I already know this from the theory. So let's look at the row space first. Row space, which we denote as CAT. So the row space is simply linear combinations of these first 2 rows, right? So I can write it simply as this: 1, 3, 5, 0, 7 times some alpha plus beta times 0, 0, 0, 1, 2. I clearly don't need the third one because it's just zeros, and 0 I already have there because I can pick alpha 0 and beta 0, right? So this is exactly the row space. I guess I could write it like this for alpha in R, beta in R. So how about the column space? So I said if I want the basis of the column space, all I need to pick is the columns corresponding to the pivot elements, which is just this. So I can write like this. In both cases, you can see that this is dimension 2, right? I have two linearly independent vectors that generate the entire space, right? Clearly, the span of all the columns can always be written like this. Similarly, the span of all rows can also always be written like this. Now, how about the null space, which is over n of A? So that means I need to solve this equation. I need to find all special solutions to this equation. So if you remember from Friday, the way I do it is that I have my free variables x2, x3, and x5 are free variables. And I can choose them in any way I want. So x1, x2, x3, x4, x5. So the first one, my first choice will be 1, 0, 0. And from this I just substitute the x2, x3, and x5 values, and I solve the remaining, the pivot variables. In this case, I need to do it quickly, so I do it on time. In this case, I will get this. So these I picked, and these I computed from these equations. The second choice will be, as you know, 0, 1, 0. So these are again fixed. I pick them and I compute the remaining ones, and the remaining ones look like this. So this is vector number 2. Vector number 3 will pick 0, 0, and 1. And I will compute what has to be the rest so that this system of equations is satisfied, and it turns out it has to be this. So you can substitute, you can just try to multiply, and you will find out that it works, because so let's try like this one. It would be minus 7. This goes with 0 and plus 7, so that's 0. That's fine. And multiplied by dot producted with the second row, it also works, right? It's minus 2 plus 2 is 0. So you can verify that this is indeed correct. So how can I write the null space? The null space can be written like this. I take the first vector, minus 3, 1, 0, 0, 0. Second vector, minus 5, 0, 1, 0, 0. And the third one, minus 7, 0, 0, minus 2, 1. So this is the null space of A. What is the dimension? Dimension is 3, right? So in general, remember, dimension has to be n minus r, which in our case is n is 5, r is 2, so that's 3, right? So in this case, we have 3-dimensional null space and 2-dimensional row space. So how about the last guy, the left null space? Turns out to be simple. So the left null space is defined as yta being 0. So what does that mean? That means that if I take y1 and I multiply it with this, y2 with the second row of matrix A, and then y3 times the final row, which is boring because it's all zeros, and I have to get all zeros out of that, right? So how can I pick y1, y2, and y3 so I get all zeros? Well, obviously y1 has to be 0, right? There's no other way I would get 0 here. So that means that y1 has to be 0. y2 has to be 0 as well. No other way I will get 0 here, right? And y3 can be arbitrary. Right? So what that means is that the basis of the left null space is just 0, 0, 1. In general, if I had more 0 rows there, then I would just put more vectors here. Like I would put like 1, 0, and so on. But in this case, it's just 0, 0, 1. So it's just one-dimensional. So I guess I could just give it alpha, and this would be all the vectors in the left null space. And again, what the theory dictates is that the dimension of the left null space has to be m minus r, where m is the number of rows. So here it's 3, minus the rank is 2, so it's 1. So that's correct. Right? So you can notice here that if I'm looking at the matrix as mapping from R5 to R3, so my A is actually a mapping from R5 to R3, then this R5 splits into two pieces, splits into the row space, CAT, and the null space, NA, right? Those are like the five-dimensional things, right? The row space was a 5-dimensional thing, and the null space was also a 5-dimensional thing, right? Just by the way it multiplies, right? All the vectors in the null space go to 0, and all the vectors in the column space, they go to something non-zero. The same way the R3 splits into 2, and it splits into the column space and the left null space, NAT. And the dimensions have to work. The CAT has dimension 2, NA has dimension 3, so 2 and 3 is 5, that works. And CA is 2 and NAT is 1, so that gives me back 3. And these always have to be equal. This is always just rank. So this works for any rectangular matrix. In general, the picture for like an arbitrary matrix, because this was just an example, right? So you could be thinking, what if I pick like a different numbers in that matrix? But this is what works for any matrix, and this is the 4 fundamental subspaces of a matrix. That was the point of this lecture. I will return to this back on Friday to give you some more comments about these 4 subspaces associated with any matrix, because that's a way essentially to understand what an arbitrary matrix does. Okay? Hope it wasn't too confusing. Thanks.